So we talked about common collector topology here, what we call a buffer. And if we have, let's say, a current source here, it's going to have an infinite impedance this way, right? We all know that much from our circuit theory. So looking this way, infinite resistance, right? So what happens now is if we have a large resistance here, our output is going to follow our input. So we just have a gain of 1. Can't get higher than that. So we call it an emitter follower. The emitter's going to follow our source pretty much at a 1-to-1 ratio. So this is ideal. If we can have something like this as a buffer, it's fantastic because as we talked about before, sorry, I'm going to try not to cover the board here, but our input resistance is going to be R pi plus beta plus 1 RE, right? So our RE, which is this thing here, is infinity in infinite input resistance, right? And now, go back over here. Now if you look at our output, looking in, right, we're just going to see infinity in parallel with 1 over GM, right? So 1 over GM is going to be smaller than infinity, so we're just going to see 1 over GM. So 1 over GM. And as we talked about from before, we have an amplifier. We don't want our load to affect our amplifier's gain. And it's something we talked about at the module 1. Right? The last problem where, now if you have a load, what does your gain look like? You'll get RC parallel RL. It's always going to be less than RC. So instead what we do is we say, let's insert a very high impedance block right after our amplifier. This looks like infinity from this, right? That looks like infinity. This is great. This means now that our gain goes from right over here, GM RC parallel RL, to just GM RC parallel infinity, which is just GM RC. So we get the maximum gain possible if this is infinity, or it's very large. Now if we look back from our load, we don't want to see a very high impedance this way. We want to see a short. You can think of it like, from the perspective of the load, right? We want to see a source. So we look this way, we want to see our source, right? We just want to see something that just looks like, say it's like a voltage source, and this is our load. Right? So in reality, we don't want any impedance here. We want to see a short from our source to our load. So in reality, if we have this, buffer here, we're going to see 1 over GM looking back. So we'll kind of just see a resistance of like 1 over GM. So this is still really small, but it's not 0 per se. It's a really small value. Similarly, if this is like 100K, as we did for module 1, we're still going to get GMRC. It'll be a little bit smaller, but 100K is still pretty large. So that's the idea behind the buffer. Any questions on that? How it kind of isolates, yeah.
Could you just re-explain why the input impede or the output impedance looking in is 1 over GM?
Yeah. So we have. So we look through the emitter, right? Right. So our source is R pi. And we are going to look up this way, right here, right? So we're going to see in parallel, and effectively R pi in parallel to like 1 over GM parallel with like RC. But R pi times GM is going to be much greater than 1, so you can ignore the R pi, ignore the RC, and then you effectively just get 1 over GM.
Got it.
Yeah.
Thank you.
And then this is infinity, right? So infinity parallel 1 over GM. Yeah. If you want, you can go through and do this derivation, but it'll simplify down to 1 over GM. Okay. So we can't always get this.
A question.
Yeah.
This is just kind of like a symboling question, because like for the amp, you know how the symbol's like a triangle?
Yeah.
For the buffer, is it also like a triangle, or is it like a
You
specific
can write it as a triangle.
Okay.
Unity gain.
Okay, yeah.
Doesn't really matter.
Yeah, you just write it. Okay.
Yeah. So can't always get infinity, right? Infinity is a very ideal number. So what do we do instead, right? We still like this topology. topology is still very good. But when we tend to make current sources, they maybe have a high resistance to infinity. So what we do is we just say, okay, let's replace this current source with a very large resistance. I'll move out of the way. Yeah. Hopefully everyone can see that. I might redraw it over here too. Can you see it already? Okay. You just replace this thing with a resistor RE. And now your gain equation is this. RE over 1 over GM plus RE. Can you see it? Okay, cool. So let's think about what happens if we make RE super large now. If we make it infinity. Can anyone tell me what the gain might be? This equation here. RE is like infinity. Pretty much 1, right? So that's where we get this. Right? So for all intents and purposes, in real life, you can't get RE to infinity. So we'll say it's a very large number. And can't make it too large, otherwise, we'll just end up turning the transistor off, right? So we want to have a good enough value. So in reality, you'll often have buffers that, if you're lucky, get like 1/2 or 1/3 as their quote-unquote gain. So you don't really get a gain, but you still get the nice properties, high input impedance, low output impedance. So roughly 1/2 or 1/3 is pretty good. So the way you now design something is, let's say you just wanted to make an amplifier with like a gain of 10, but then you want to have a buffer there to isolate the load from the amplifier. Instead, what you'll do is you'll design a buffer for a gain of maybe like 1/2, ideally, and you'll try to double this gain. You get 20 times 1/2 is still 10. And that way you can still have good gain while benefiting from this high impedance this way, low impedance that way. That's how you kind of counter design. So first part of module 3 will have you design a buffer, and will give you, certain specs you have to meet. One thing it'll have you do is you make certain requirements for input and output impedance. And one thing I've not drawn here that you still have to keep into account, right, is you still have this resistor network here to bias it, right? R1 and R2, just like you did for the common emitter, right? Now, just like module 1, if R1 and R2 are large, you don't have to worry about them, they're just there for biasing. But for module 3, you'll realize that if you want to meet these certain input-output impedances, you have to lower R1 and R2 such that they now take into account, in the small signal model, you'll see your R1 and R2. So in other words, you can't just make these like super large, like 10K we did in the first one, and not have to worry about it anymore. If you try making them 10K to your input-output impedance, you'll see that you can't actually get the right values. You get one, but not the other. The only way you can get them both right is if you lower R1 and R2. So again, just like on module 1, you had to like tweak values after you use your equations. Same idea, except now you got to tweak R1 and R2 instead of like RC and RE. And there's no RC for common collectors. Yeah, these tie straight to your VCC. Any questions on that? Yeah, that'll be the first part of module 3. So this is just your topology, your basic topology. So you have a resistor here, and that's all you'll be doing. So that's module 3, first half. Any questions? It should all be like review from 115A and or lecture 1. Cool. Okay. So now we talked a little bit about, in wrap, what are we trying to do? We go from 1 megahertz to 5 megahertz to 27. How do we go there? Why do we need to, etc., right? We've been talking about amplifiers, but no notion of like frequency apart from like those random capacitors we had, right? Let's not bring frequency into the picture. In lecture 4, which is going to be start of winter, we're going to talk about mixers and how we can upconvert in frequency. But for now, we need to talk about how do we generate frequencies. I mean, we always talk about this notion of like frequency and like 102 and stuff like that, but like, what is a frequency? How do we like physically make it? And how do we get it stable? We can have like, draw this out here. So can anyone tell me what like a frequency would look like? If you just have like a 1 megahertz signal, what does that look like? Benji? What is it? What's that? What's the name of that?
It's a wave, a
It's a wave, a sine wave. Okay,
a sine wave,
good.
or cosine wave, I don't know.
It's a sinusoid. Alright, so like ideally we want something looks like this, right? This is, well, it's a little messy, but you know, we'd say this is like one frequency, one tone, right? And the frequency domain, well, this is a sine, but that's kind of complicated, but I want to introduce a complex magnitude and frequency domain for some of you. That might be kind of confusing, so let's make this a cosine instead. Okay, so in the frequency domain, so it's magnitude of x. Okay, so if this is at a frequency, let's say omega naught, you'll have, you know, like one peak over here at omega naught, and one over here at negative omega naught. Same amplitude. This is what we refer to as a single tone, single frequency, right? If you had two of these cosines, one at, you know, omega naught, one at 2 omega naught, you'd have something over here at 2 omega naught, and then again at negative omega naught. So you just add them up, right? That's one of the properties of linearity, is to add up signals, right? Add up sinusoids in time, just add up in the frequency domain, right? So we want to somehow generate a very clean, let's see, we'll generate a very clean sinusoid. So in the frequency domain, we want to see peaks like this. If we see stuff like up here, that, you know, it gets messier. It's not really a P or sine, all right? So we want to somehow get this picture. Okay, everyone good on that? Okay, so the next thing is this something you've encountered in like circuit theory or maybe like in physics that, you know, oscillates? Anything that you'll have a back and forth trade of energy. Think of some elements we know of, like resistors, capacitors, inductors, transistors. Eli?
Capacitors.
Capacitors?
And
Okay.
inductors.
Exactly.
LC circuit.
Yeah. So, what we're going to do is we're going to have effectively, well, take one step back. We just have a circuit like this, right? And let's say we just charge up this capacitor initially. We hook it up to this inductor, right? What's going to happen is we're going to store energy in our electric field initially, and then this energy is going to dissipate through charges leaving the capacitor. That's now going to build up energy in the magnetic field of the inductor. That's then going to then dissipate it back to the capacitor. It's going to be in a very cyclical nature, right? And this actually just looks like sinusoid here. So this brings us to the notion of if we can create an ideal inductor and capacitor, we can just have a perfect sinusoid, one frequency. Can anyone tell me a problem with trying to realize this in life? Megan?
Inductors aren't ideal, they have resistance.
Okay. Cameron?
Yeah, I was
Resistance?
just gonna say
Yeah.
the resistance dampens the oscillation.
Yeah. Antoine?
The inductor has a self-capacitance, so it can
Yeah.
resonate with itself.
It could. But let's not go into that detail. Let's just talk about assuming just resistance, okay? Generally speaking, we just assume the inductor has series resistance that's parasitic. Capacitor does too, but it's not the same. You'll end up just adding them in series anyway. So I'm just gonna call it RS, right? So something looks like this now. What's going to happen is our wave will not be a pure sinusoid, right? We're gonna be having, you know, electrons go from here to here, and then some are gonna dissipate through here, and we're gonna lose power over time, we're gonna lose energy. The system only has enough energy at the start, right? There's a finite amount. So as, you know, carriers move back and forth from the inductor to the capacitor, they'll go across the resistor, and, you know, energy will be dissipated in the form of heat, right? So what's going to happen, I'm gonna try and draw this out in a one clean manner. We're going to have damping that, like you said, keyword damping, and it's going to maybe look something like this. It's kind of exaggerated, but eventually we're going to start losing energy and our amplitude is going to decrease, okay? And now, if you link the equations here, those of you who are interested, this is the general LCR equations. right? So. This is V0. This is time. So we're just saying initially the capacitor at time t equals 0 minus is this has some voltage across it, V0. And then we have to create equations now. Okay, so this looks kind of scary, right? But this is just, if you plot this is just cosine, right? What this does is it takes care of that decay over time. And these are just correction terms because you have an RLC circuit now. So if you just see this, just know it just looks like a cosine, but it's over time the amplitude is going to decrease to 0. And you have a few expressions for this, omega d is alpha. Okay. So we're not going to be using any of this, by the way. It's not, don't want to scare you, right? But these are just the underlying equations that you'll have for an RLC circuit that you'll very much end up using in, 10 or definitely 110 for sure. So, okay, the conclusion we have now is we're going to generate one frequency. An LC circuit can do that, but we know that we're going to have some parasitic resistance that we can't get rid of, that we have to deal with. How could we, I guess, account now for parasitic resistance? We've accounted before for if we had a buffer, gain of 1/2, so make the amplifier 2 times stronger, right? We're gonna have a kind of another solution that we use here. Okay, so let's say we have, I'll draw it like this. Okay, so what we do is we say, okay, we have this RLC circuit. We will measure what this R is, and we're going to shove some negative resistance in there that's equal to that. So now if you just do, you just add these all up, you'll get this R plus minus R, so we have 0 resistance. We still have, reactance due to these L's and C's, but we don't burn any power. All right, everyone kind of.
Negative resistance.
That's the crazy thing, right? What's a negative resistor? We'll talk about that. But does this concept make sense? We account for these parasitics, and now we're like, okay, we gotta get rid of it somehow. We can't get rid of it, but we can negate it, right? That's something you'll see a lot. We can't get rid of something, so let's do the opposite, right? It's still there, it's still inherent to our system. We just do something that it's as if it wasn't there to begin with, right? Now, negative resistance, that's weird, That's like us generating energy. How do we do that? Well, what do we do with transistors, right? We amplify, we generate energy. So it kind of brings to an idea that we can somehow use a transistor here to get negative resistance. Just like how we have to use a transistor to get gain, because we can't get gain with just resistors, capacitors, and inductors. We need something else in there, an active element. So transistors are like the key here for negative resistance. And luckily, we've already kind of covered a way to make a negative impedance. This may not be very obvious. I guess any questions on this so far? The negative resistance, why we need it, how it comes about? Nothing? Okay, cool. So, I'm gonna do one big step here, okay? We're going to now go to a circuit that will generate one tone that's output, one frequency. It's gonna look a little scary, okay? We're gonna have some L's and C's, we're gonna have some R's, we're gonna have a transistor. But we'll walk through it, we'll solve it in 2 different ways. We'll first solve it with all the lengthy circuits algebra, and the second way will be with 141, if you've taken it. we're gonna be doing feedback. So we're just gonna talk about, in a feedback loop, what are the criteria for oscillation? So those of you who've done 141, hopefully the second one will be an easier approach because you don't want to do the first one all the time. Okay? So this topology, we call it a cold pitch oscillator. There's various types of oscillators. You have like Hartley oscillators, Pierce oscillators. They all work the same way, just generating a negative resistance. The question is how do they do it? So first, I'm just going to draw it all out for you. Okay. Okay, so looks kind of scary, right? We have this, this buffer, right? You can see it here because it's in the output out the emitter, and our input signal is going to stay over here, right? So we have some signal, it's over here. It's then going to ideally, be multiplied by 1 to V out. That signal is going to be fed back over here. We're going to do some things to it, and then it's going to be fed back in over here. Now, at a first glance, we cover this up, right? This just looks like an LRC circuit, so we expect some, frequency when we resonate, right? So the goal of this circuit is to, this part takes care of the negative resistance, and that part takes care of generating the frequency. Everyone kind of see that? Okay. So for those of you who have not done 141, the notion of feedback is a little scary here. Looks a bit weird, but it's the idea that you have a system, you put in the input, you take your output, and you feed some of that output back to your input, just to allow for correction. Something we call, in this case, negative feedback. Positive feedback in this case, if we're making an oscillator. But feedback comes in many forms, negative and positive, and if you keep doing more circuits, you'll learn more about it. So the idea here is we have this, we can simplify this just a little bit. What we have, right? From the perspective of that inductor and that resistor, we just see some network here, right? They don't know that there's capacitors, inductors, there's capacitors, a transistor there, the R1, R2. They don't really see that. They'll just see the net result of that network. So the question is, let's figure out what they see. All right, so this, you want to find impedance looking into this network. Any questions so far? It's kind of like a black box approach. We have some system, we know some of it. Let's see what the rest of it looks like. This is like your Thevenin and Norton equivalent in a way. Any questions? So now we get into a lot of, can I erase this? Get into a lot of tedious algebra. You won't be expected to know any of it. You'll have to know the final result, but yeah, I don't expect any of you to ever go through all of this and do the proof. But we're just going to do it one time now. Okay. So first, that's way of doing it. Okay. Make a few assumptions here. Just like module 1, we assume R1 and R2 super large. We can just ignore them in our small signal model. Okay. Next thing we do. That'll be kind of, I'll draw it out first. Okay, so we just ignore R1 and R2. And what I'm doing is drawing the small signal model of our network here. This side, ignore R1 and R2, have an input at the base, and see what the rest of it looks like. if we follow that, we'll see something that might look a little scary. Okay, so I'll write down our assumptions here. First is that R1, R2 are large, so they don't show up in our small signal model. Second thing here that's kind of weird is that we don't have an RPi anymore. Reason being here is that we design our system such that if we were to have an RPi, it would show up over here in parallel with the C2. And the idea is that we design it such that the impedance of C2 will be a lot less than this like RPi, so you effectively just won't see RPi at all. It's still there, it's just C2, that impedance of C2 is so small that it effectively just removes our RPi. So it's a bit weird to see, you know, we have this RPi that's always been there, and now we're just neglecting it. But it's still there, it still happens that it's effectively shorted. If we were to include it, it'd make all our math a lot more complicated, okay? Now we want C in equals Vx over Ix. And we want to, now solve for all of this. So I'm going to write down a lot of equations, and for those of you who are familiar with the Laplace transform, the Laplace domain, we're just going to be representing the impedance of these capacitors in the Laplace domain, okay? So what's the best place to be doing this? I'll do it over here. Okay, so this is some capacitors C. We have that impedance of this capacitor domain 1 over J omega C. All right, everyone knows that. In the Laplace domain, this is 1 over SC. So it's what we're going to use for the impedance. That way, we just don't have to, deal with more of the tedious math. We can just say 1 over SC is our impedance. Other thing about the Laplace domain is everything's going to be linear, so we can only go there where things are linear. Again, kind of ties back into the whole small signal model being linear, so just makes our math a bit easier. Okay, so equation 1, I'm going to do, we know we can do a KVL here. Okay, let's call this VE, right there above this capacitor, right? So we know that V pi will be equal to Vx minus VE. So we just go from here, this is at Vx, right, minus V pi equals VE, right? That's how we get this. So it's equation 1. Now equation 2, which gets a bit more complicated, is we're now going to do a KCL at this node. So I feel like I'm blocking it. We're going to do KCL at that node. So we're going to have some current going this way, some over here, some over here. Just going to sum all of those up. Use a different color for this. So we get S1. I guess I'll do one thing first to not confuse anyone. If we have, draw it over here, capacitor and capacitor positive V. If we want to find the current through this, right? What's going to happen is we get V over I going to be equal to 1 over SC. So we get that I is equal to SCV. Okay, so you may find it weird because if we had a resistor, right, it would just be I is equal to V over R. But because being with a capacitor, it's the inverse, so we have SC times V. So don't get confused by that. It's very tricky. So we're going to just, don't get confused by that. Okay. So over here, if we look at this, the current going down, if we apply this idea here, the current going down here, it's going to be SC1 VE. Any questions on that? Okay, cool. SC1 VE, and now we're going to say, we're going to add, so we're going to have this current here, okay? So it's going to be SC2, okay? And now we're going to have VE minus Vx now, one more term. Specify drains, okay. Minus PM times Vx minus Vt. Okay, so that's that. Okay, so that's our KVL and our KCL. Go over here now, and I'm just gonna write down all the simplifications and get to our final result. Okay. So now, we get this equation here, and we can now just move this denominator up there. Okay. So finally, we get this equation for our input impedance in the Laplace domain. 1 over SC1 plus 1 over SC2 plus GM over C1 C2 S squared. And I don't expect any of you to even memorize that step or any of the steps before. It's just a long derivation of it. For those of you who are curious as to how we got that, just these two KCL and KVLs. And then you do partial fraction decomposition here. So if you want, you can go through and do it yourself, but only do that if you're really bored. Okay. So now we take it back to the frequency domain. And we're just all the S domain, right? We now say, okay, S is equal to J omega. We get you'll notice something now. I'll try and move out of the way. So these two are still positive, right? These two C1, C2 terms, just like these two. But now, this term is negative. Can someone tell me how the negative came about?
S squared.
Exactly. So we plug in J omega, J squared is -1. So now we just get this minus sign in front. You can see how we get some negative impedance now, right? So everyone follow that so far? Okay. So this is our term of interest here. Okay. So in other words, you think of this as your negative resistance, and these are all your energy storing components, right? C1 and C2. They store energy. They don't really do anything else apart from that. This is what we can use to, in this case, generate power, right? A negative resistance. And I'm gonna erase. Does everyone have this part and or this written down? Can I erase it? Okay. Let's erase this part for now. So now let's draw an equivalent diagram for that input impedance. Okay. This is going to be right? These are effectively like capacitors in series. So that just add capacitors in series like resistors in parallel. And now for this, the value of this resistor is this negative GM over C1, C2, omega squared. All right, and just going from that equation to this picture. Okay, everyone follow that? Yeah. So now I'm going to make a few bigger steps. Okay, we talked about before, if we have like an LC circuit, it's going to resonate at a certain frequency, right? Just like before, we want this network here to resonate. So when it's hooked up to the transistor, we want it to also still resonate. Resonance is equal to just generating a frequency. You can think of it like that. Okay. So at resonance, I'll do this over here. So can someone tell me about, let's see, I guess at resonance, what happens to the impedance of your capacitor and inductor? Let's say you have a series inductor and capacitor. I guess let's say you have something that looks like this. So at resonance, what does this look like? I'll give you a hint. At resonance, these are series. This will be a short. 0 ohms, right? So what can you tell me about these the values of these impedances relative to each other?
Get each other.
Opposite, right? So this is like has an impedance of like R. This is called R. This would be negative R, vice versa. So one's negative, one's positive. They subtract, you get 0 at resonance. If these were in parallel, right? What kind of happens here? Anyone? Think of what's the equation for things in parallel? Any two objects in parallel.
So oh,
What?
the denominator becomes 0.
Yeah. The denominator becomes 0, infinity. Right? So now this looks like infinity.
So is it an open circuit?
Yep. Yeah. So this is something you'll maybe learn, I guess, in 110. But it's good to know this now because interviewers love to ask this question. If you tell them, hey, I've done circuits, you know, like one circuit theory class, we'll probably ask you this question at some point. So that's important, so just remember this. There's series, short, parallel, open. You can always fall back on the equation for two things in parallel. Two things in parallel, it's just they're multiply them together and just divide by the sum. So as everyone understands, this is infinity, right? Okay, cool. So next step now is, let's say that's at resonance. So remember, we can just shove that circuit in blue right over here, right? Because that's what we were solving. What does this look like? It's like a Devon Norton equivalent. We can just shove it in there now. Nothing changes. So if we do this now, let's rewrite it here. Get something that looks like this. you get something that looks like this. So now when this resonates, right, we expect these two to cancel each other out, right, because they're in series, right? So at resonance now, we get that this is positive, right, and then the capacitors will be negative, right? Or you can do vice versa, the sign doesn't matter, right? But the idea is you add them up and you get 0. Right? And I've called this C effective. It's just this. Again, it's like a partial fraction decomposition. It's in reverse. Okay, and now we want to solve for omega naught. And here's what I'll do. I'll do omega naught squared is this. Does this equation look familiar to anyone? Right? Who could tell me what it looks like? Ben, do you look like
It's
you
that
know?
like, it's that 10 equation, I remember that.
Yeah.
Time constant? No.
It's just the resonant frequency of an LC circuit.
Yeah. It just, we have to see effective, but like,
Yeah.
just the name, right? We do the square root here. Right? So it's the same thing we've already seen before with this normal LC circuit. We did all this complicated stuff, you get the same response, right? You can also think of this as like when you take a definite equivalent, right? Or any equivalent, you're gonna end up just seeing resistances, inductors, capacitors. You're not gonna see a transistor as an equivalent, right? That doesn't make sense, right? So always gonna see some resistor, capacitor, or inductor. So it makes sense that you can always make some equivalent capacitance, some effective capacitance, some effective inductance to capture a network. So it makes sense to always be your equation, at resonance, right? No matter how many of these, if you have like another capacitor here, you have another inductor, it won't change. All it'll change is what these effective values are. Your base equation stays the same. Pretty cool. So this is something that you'll use a lot, circuit classes. Black box, look in, what does it look like? Shove it back over here and make some assumptions, see what happens. Yeah.
So what about like, how do we, okay, sorry. For like, let's imagine like with a BGT, with the transistors, we usually have like parasitic capacitances,
Yeah.
right? So like, how does that impact our oscillator circuit?
I'll talk a little bit about that.
Okay,
It gets slightly more complicated.
okay.
Won't do any of the math for it, but conceptually I'll walk through it if we
Okay.
have time. Yeah, that's a good question because for the new crystal oscillators we have, this extra information. We pick our C1, C2 values in reference to what the capacitance of the transistor looks like. So the junction capacitance, base capacitance, etc.
Yeah.
So we'll get to that. So that was the imaginary part, right? At resonance, what happens? So at resonance, what happens to the resistance, the real part, right? So we'll get something that looks like this. That, hold on. Few things here. If we would just add those together, right, we ideally want to get 0. So that's where this kind of, typically this would be the second equals, right? But we're just saying this GMC1, C2, omega naught squared comes from all the way over there on the right, same term. And, well, if these resistances are going to be equal, we can just make this equation the same magnitude of it, right? Just take the positive. So, in reality, what happens is maybe we want this to be larger, this negative term to be larger than the positive term. So now we don't just get stable oscillation, but we get like growth over time, right? In reality, you don't want this, but you want to at least design for it because then you can be able to tweak things. But it's important to understand that if you have more negative resistance than positive, you're gonna get growth, and if they're equal, you'll get a stable sinusoid. we want stable sinusoid in this case. So what we'll do is we're just gonna say, okay, GM over C1, C2 omega naught squared is this gonna be equal to RS, right? And now we can solve for GM. And that's it. So that's all we gotta do. Bias our transistor such that we get this value. Alright? Just like how in module 1 we said GM is like IC over VT. We were given IC, we knew what VT is, and calculate GM. Same idea here. So for a particular parasitic resistance for particular C1, C2 values, and if you're aiming for a particular frequency you want, you can figure out what your GM should be. Once you figure out what your GM should be, I erased it, but you can bias a transistor appropriately, right? Just remember that picture, we still had an RE all the way at the bottom, so that's how we can still bias our transistor to get that GM. So the design flow is we want a certain frequency to operate at, omega naught squared. Omega naught is going to be 2 times pi times frequency of interest. Multiply all that by RS, C1, C2, get our GM. Alright? Now, what's one way for us to, kind of fact check derivations we've done so far are correct? Let's say like, in the ideal case, we'd have no RS, right? We would just have an LC network. That's gonna oscillate perfectly. So if RS is 0, we get that GM is 0, which means we don't even need the transistor to begin with, right? That's the idea. So we can verify it like that. Okay. So the next thing we're gonna talk about is doing all this complicated math before with feedback. But we're gonna save that for after the break because I think this is already quite a bit to digest. But any questions on anything so far? Because once we get to feedback, all of these things will be extracted. We're not even gonna talk about like impedance. We're just gonna talk about feedback, and we'll get the same equation somehow. So that's really cool. Any questions now, please ask, so that when we get to feedback, it's like, okay, you kind of see how things have translated. Yeah.
This might be out of the scope of the lecture, but like conceptually, how does the negative resistance work?
How does it work? Okay. So you're good with like how we have this Z in. We
Yeah.
solve for it, right? That's all good. Okay. So what's happening is the transistor is going to, in a way, like, I won't say amplify. It degrades our signal technically because it's a buffer, right? But some of that gets fed back into our feedback path. I'm going to use the word feedback here because it's hard to describe it otherwise as a negative impedance. So it gets fed back, right? And what's going to happen is it's going to constantly keep feeding things back, right? But the only signal that will persist throughout the system is if it's at that frequency at omega naught. Because only frequencies at omega naught will satisfy such that these resistances cancel each other. So it's in a way, we're not making a negative impedance, like we make a negative impedance, but this changes with frequency, right? The only way it perfectly matches is at resonance. Yeah. So this is just a result of the way you have the feedback between the output of the transistor kind of going back in. It's also partly a result of, in the small signal model, which is now erased, you had the C1 shorting R pi.
Is that why we have like this short between
Exactly.
V naught and
Yeah.
Okay.
Yeah. Take
Makes
it back,
sense.
back in. Yeah. If we consider that R pi, we would have to do a bit more math, and we would need a larger GM. But yeah.
Could you explain, like, conceptually why the inductor and the capacitor in series would have like no impedance at
Yeah.
the resonance, while if they're in parallel they have like
Yeah.
infinite what do you call it, impedance?
Yeah. Okay. I'll do it over here. Can I erase this? Everyone got this? Go. So what's the equation for the impedance of an inductor? We know it's complex, so I'll just write the J out for you. Right? Yeah. And these are in series, right? So we can just add the impedance of this.
Negative J 1 over omega C.
Yeah. Right? So now the idea is if we what's it called, just apply an input signal, look at the output. Let's just say we want these to be, it's kind of circular reasoning, but let's just say, okay, let's flip the plus away, right? So we're just gonna say these are 0, right? Because the idea is, okay, we apply an input signal, we'll see that we'll get a current going through that's gonna be equal to this drop, and then this drop, right? Actually, I'll just do that. I'll do the whole thing. It's around. Okay, so we're gonna get that x is going to be equal to, let's call this I, ix, times j omega L. Okay, we have this equation, and what we notice is that we can move this negative over here. And I'll move the j outside too. All right, this is our equation. So now we can say Vx over Ix. I'll just call this Z. It's going to be you get this, right? For the impedance looking in. So now, because this is negative, engineers for some reason like to find where things go to 0. We're like, oh, where does this go to 0? And then we say, okay, well, we solve for this part being 0, right? That's how we get that resonance frequency. So this just tells us at 1 over square root of LC, plug this in, that goes to 0. That make sense? It's just this equation here, but yeah. And then, does that kind of follow? We get that equation. It feels circular. It feels like we have to know it goes to 0 to even try doing that, because otherwise why would you do it? Like I said, engineers like to find where things go to 0, so that's why. So that's the equation. They're like, oh, where's it go to 0? And you solve, and it just, okay, at resonance, that goes to 0. Yeah. And then similarly, if we know these are in parallel, because if these things are in parallel, all right, I'm just going to use a shorthand notation here. Right? This is the same thing as this, right? So then at the same frequency, this goes to 0, right? So then this will just be some negative number, right?
Yeah.
And negative divided by 0 is infinity. So that's how you get that. That does feel a bit weird, but the idea, because you use this conclusion to then say, okay, given this, that happens. But they're both one and the same. Yeah. We'll do a break for like 5 minutes, and we'll get back into it.